Step one in almost all IMF problems, multiple choice or free response, is recognizing what types of IMFs a molecule may have. Step two is comparing them in terms of their strength. And then step three is often using the properties to compare that substance to another. So here we've got a key for our drawings to recognize that here I have a pure sample of HF. That has dispersion forces because there's molecules, dipole forces because the polarity is large enough, and hydrogen bonds because the H is directly on the F. F2 has only dispersion forces, no polarity, obviously no hydrogen. When I put a sodium ion in water, there would be some dispersion forces, but we really focus on, in a mixture like this, the ion to dipole force. And remember, that ion to dipole force is fairly strong and often even stronger than hydrogen bonding or other types because that sodium has a full +1 charge. In SO2, we have a bent molecule. It is asymmetrical, so that is a polar molecule. There are dispersion forces and there are dipole-dipole forces. If we were going to kind of compare one of these to another, the F2 with only dispersion forces would likely be the overall weakest of the attractions. SO2 would be greater and HF would likely be the next greater, but we do need to account for SO2 having significantly more electrons than HF. So maybe a boiling point, vapor pressure, or another piece of data would give us a little bit more clarity as to whether the dipole and dispersion here are enough bigger because of significant polarizability than even the hydrogen bonding with HF. But the ion to dipole force is definitely going to be stronger Na to water than HF to HF, and likely stronger than any dipole in the others. In the next, we've got silicon trihydride, we have ammonia, we have nitrogen trichloride, and we have the element or atomic krypton. SiH4, if you draw that out, is symmetrical. It is very similar to CH4, and it would be all nonpolar with only dispersion. NH3 has dispersion because it's a molecule, dipole because it's trigonal pyramidal, therefore asymmetrical and polar. It has hydrogen bonding because the H is directly on the N. NCl3, kind of stumbled over that, I apologize, has dispersion, but once again, it's trigonal pyramidal. It has dipole. One thing to note compared to some previous is that this has significantly more electrons than that. Lastly, krypton has only dispersion. There's no polarity and obviously no hydrogen bonding. So the SiH4 is most definitely going to be the weakest in terms of overall attractions, lowest melting and boiling point on that, probably highest in terms of vapor pressure because it would evaporate easily. Krypton is also very low. It's a gas, so we know that that attraction has to be weak because the molecules aren't held quite as tightly there. NCl3 and NH3, the hydrogen bonding would lead us to predict that this could be significantly stronger, but there are 40 to 45, maybe even more than that, additional electrons in the NCl3. So we have to be open to the idea that even with the hydrogen bonding, the dispersion forces could be so great on that NCl3 that we would see a little bit more attraction to itself. So we look for general trends, but then once we get into those specifics, we do need to think about number of electrons, compare those, and look at data for a final difference.